Hello and welcome to homework 4, part 3. In this part of the homework, what we're going to start out talking about is something known as the bode diagram. And this basically piggybacks off of part 2 of this homework. And where we ended there was that we had a sinusoidal function going into our control loop into our forward transfer function, and our output was therefore a sinusoidal function as well. But what we saw here was that we had our output function here in the blue and our input function here in the red. And what we do not want to see happen is we don't want to see the amplitude of our output curves to be greater than the amplitude of our input, because then that means our system is going to be unstable. So when we talk about this ratio of the amplitudes, it's called the amplitude ratio, and essentially another term here is called the phase lag. And basically it's the difference in angle between the top of our output curve and the bottom of our input curve. So when the phase lag is 180 degrees, we don't want our amplitude ratio to be greater than 1, or we could run into instability issues. So the way that we can predict these things, phase lag and the amplitude ratio, is by taking a look at something called the bode diagram. And we can actually plot the bode diagram for our forward transfer function in the control loop that we talked about in part 2. So what we're going to do to start off part 3 in the first part is to actually plot that out here in Python. So if I do sig.bode, we can actually just supply the transfer function that we want to take a look at. And what this bode diagram will output for us is the frequency, the phase lag, and also the amplitude ratio. So I'm going to go ahead. What we're asked to do here is supply our forward transfer function of that control loop. So I'll supply that, and if I press Shift Enter here, what we basically get outputted is 3 different arrays. And what this is that these values here are the frequencies. The second array is the amplitude, the magnitude of the amplitude ratio. So that is the second array, and then the third array here is the phase lag here. Okay, and what is commonly basically the amplitude ratio is denoted by is dB for decibels, because that's what it's returned as. So let's go ahead and unpack this. We'll have W for the frequency. That's our first array. Second, we have our decibels for our amplitude ratios. And then lastly, we have our phase lag. So what we can do here is grab all these values and then go ahead and actually plot this up. So I'm going to go fig is equal to make subplots. And how these plots are usually made is basically right on top of each other. So you usually have, the way I've seen them, just looking them up, is the phase lag is usually on the bottom, and then the amplitude ratio is on the top. So we'll do rows is equal to 2, and then just one column. Columns is equal to 1. And then we'll do fig.add scatter. Our x values will be at our frequencies, and then we'll do amplitude ratio first, so dB, and then we'll set, whoops, that should be equal dB. We'll put that in our first row, in the first column, fig.add scatter, oops, x is equal to frequency again, and however this time we'll plot our phase diagram. y is equal. We'll put it in the second row. Okay. Let's go ahead and plot this out. So here is on top here. This is our blue. Looks like it is. Yeah, it's in our first row. So it's our amplitude ratio, and then in our second column down here in the red is the phase lag, and this is measured here in degrees. That's the measurement. Okay, so I noticed a couple things that I just misspoke about a few minutes ago. One is that what we are returned here out of this function here is the decibels here. So what we need to do in order to convert from decibels to amplitude ratio, I'll show that in just a second. But what we want to do here next is we want to be able to basically see at a frequency of 1 if our amplitude ratio matches up on our diagrams here with what we actually calculated here, because that can help us to know if our diagrams are actually useful or not. But back to this decibel to amplitude ratio. So what we have plotted here and is our decibel. And one thing I forgot to mention is I went back and changed, I forgot to change back our tau d from 0.1 to 0. So our phase diagram here, our phase lag, definitely looked a bit different. So I noticed that and changed that back, tau d back to 0. And then I just adjusted the height and width so we didn't have a gigantic screen of plotting. But let's go ahead and get from decibel to amplitude ratio here. And I just have decibel pulled up on Wikipedia here. And what this tells us here is that our decibel output here is this LF. And the amplitude ratio here is this F over F naught. That's the ratio that we're looking to get at. So what we need to do with our decibel output is divide that by 20 and then take 10 raised to that power because we have the log base 10. So let's go ahead and set that up. So I'll have AR is equal to 10 raised to the decibel divided by 20. So that's how we can get from decibel to amplitude ratio. And next thing, actually what I'm going to do here is what we can do to be able to see the frequencies a little bit more clearly on our x-axis is to update it as a logarithmic scale so we can really zoom in on our axis. So I'm going to go fig.update underscore, I believe it's underscore x axis, and then I'll do type is equal to log. Okay. Go ahead and run this here, and yeah, so you see, like, if we wanted to look at a frequency of 1, we can get our decibel here a lot better than if we just had a linear scale. So let's go ahead and what I'm going to do here is I'm going to go sig.bode, and we're going to try out our graphs here to see if they are what we think they are. So we'll have our forward transfer function here. And this time we'll go ahead and supply a frequency. Let me go back out, Control C, and put in a new block of code here. I'll just go down here. So what we are returned here in our second array here is in decibel, and we have a negative 3.87. So what we can do here is we can just go in and substitute in here negative 3.87. So if we do that, I'll just do 10. 10 is raised to negative 3.87 divided by 20. Oops. See what that returns us here, and I may have to do that down here as well. I'm just going to set this equal to test. And now let's see what our test looks like. So this is what our amplitude ratio is, 0.64. And if we go back up and look at what we had plotted before, our ratio of the input to the output is going from 1 to just about 0.4, it looks like. So we know that our two graphs here are definitely correct, and that's what we're asked to do here in the second part of this part 3 homework. Okay, so the next thing we're asked to do is explain a couple of things: crossover frequency and phase margin, and what that means in terms of the stability. So first to go over crossover frequency. Crossover frequency is when your phase crosses negative 180 degrees. And what this means in terms of stability is that you'll look at when your phase crosses negative 180. So here it's approximately, looks like just a little bit around 1 radians per second. And what you do is you go up to your decibel chart, and you look at 1 radians per second. And if you are below 0 decibels, then your system is stable. But if you are at negative 180 at 1 radians per second, and you go to 1 radians per second on your decibel chart, and you're above 0, that means that it is unstable. So that's crossover frequency. Now, phase margin is you go on your decibel chart here, and you see when you cross 0. So here it looks like about 0.75, 0.8. And what you do here is you go down to your phase diagram, and you go to 0.75 or 0.8 approximately, and you see where you're at. So it looks like here we're about negative 173 degrees. And the phase margin is the difference between where you're at, so negative 173 degrees, and negative 180. That's basically your room for error. So here it's 7 to 10 degrees is what it looks like. And that's what it means in terms of stability for phase margin. Obviously, as that decreases, you get closer and closer to instability. Okay, so the last thing that we are asked to do here is basically to show our system in an unstable condition. So the way I'm going to be able to do that is by raising our Kc value, so that when we go down here to our crossover frequency at 180 degrees, what we'll see here is that our decibels are greater than 0, right? Because we're unstable. And also what we'll see here in our open loop is that our output will be bigger than our input in terms of amplitude. So let's go ahead and do that. So I'm going to put our Kc at 3, shift enter. So we can see here in our closed loop here, we are unstable. So we oscillate, and the oscillations are actually getting bigger. So this is for our closed section here. And then if we go down here, let's see here. So this is, again, our output, right? And then this is our input. So obviously the amplitude is much, much bigger. Let me go ahead and make sure I ran all of these. Yeah, I didn't run that code up here. But you see here that the amplitude of our output is much greater than the amplitude of the input, which is not good in terms of stability. And also looking at our bode diagrams, we can see this as well, right? So if we go to our crossover frequency down at 180 degrees, we can see that's at about approximately a little greater than 1, let's say. So we'll go over here to a little greater than 1, and we are above 0. So that would indicate that our system is unstable. So that basically verifies what we have seen here and also here. So that will do it for part 3 of this homework. Thank you for watching.